Hello everyone, my name is Dr. Deepak Yadav, and today we are going to discuss the complex topic, that is basics of antenna for the antenna and wave propagation subject. And this is the topic from the unit number 3, in which we will discuss about the basic antenna parameters and how antennas actually radiate the electromagnetic wave into the atmosphere. These are the parameters that we are going to cover in this lecture. That is introduction of what is antenna, what is the fundamental properties of antennas, basic antenna parameters like radiation pattern, beam area, beam solid angle. This is represented by ohm A, ohm, and the A is in the suffix, radiation intensity, beam efficiency, directivity gain, resolution, etc. And in the next lecture, we are also going to discuss these topics, that is radio communication link, field from oscillating dipole, signal to noise ratio, and antenna temperature as well. So this is the structure of how the antenna is connected to the source and how it is radiate the electromagnetic wave into the space. Like if we consider this, this is the source of the electromagnetic wave that is generated, and this is the transmission line. This transmission line may be wire, maybe coaxial cable, or guided waveguide, like circular waveguide or rectangular waveguide, in which the electromagnetic field is travel from source to the antenna, and this disturbed structure of the guided medium is known as the antenna. The antenna is going to be flared up, and this flaring up of the antenna is because we want to match the impedance of this transmission line with the impedance of the phase, which is very much constant. This is nothing but 377 ohm. This is equal to 120 pi ohm. So this is fixed. This is the fixed value of the impedance of the impedance of the free channel, and this is the guided medium, which is having a very less impedance of 50 ohm. So by this flaring up of the transmitting media, we want to actually meet the impedance matching from the transmitting line to the free space by this flaring up, and this flaring up increases the impedance and the wave is going to be transmitted. So the point up to this is known as the transmission line, and the flaring up part is known as the antenna, and this is the actual radiation radiate into the free space. So as we can see over here in the guided media, the electric field vector is line up like this, and it goes from this to like this and make a circular loop, and the magnetic field is in the perpendicular direction of this, which is coming out from the board and going back again into the board like this. This is the electric field vector, this is the magnetic field vectors. So as we flare up, the electric field vector is going to be bent up like this, and in the space when it radiates from the antenna, the line is now making a loop like this and radiate into the free space. So due to this impedance matching, due to this flaring up, the wave is easily radiated from the space and making these kinds of loop. This is the electric field loop. The magnetic field loop is perpendicular to this, which is not shown over here. So what is the radiation resistance? So when the antenna is trying to radiate the wave, some of the wave is radiate as a radiation, and this is treated as a loss in the total system. So this loss is represented by the radiation resistance of the antenna. That is two type of losses over here. That is RL, that is loss due to the heating up of the antenna element or the antenna as the signal is propagate from the antenna, and the another loss is the radiation that is going out from the from this complete system, from the transmitting system to the space. So two different resistance is represented, the different losses due to the heat or the ohmic losses, and losses due to the resistance, and this losses due to the resistance is represented by radiation resistance. So if we consider the total Thevenin equivalent circuit of the antenna system, is there is a source in which the wave is transmitted and it is represented by the impedance Zg. This is the transmission line. As nothing is like ideal. So the matching from the antenna to the space is not proper, and due to this some amount of the wave is get reflected back. When the wave is coming like this from the antenna to the from the source to the antenna, and due to that mismatch some wave is going back and form the standing wave scenario. Standing wave scenario. This standing wave is presented in the transmission line, which is connect the source to the antenna. The amount of the radiation that is going out from the antenna, this is antenna part, is represented by either RL, that is the losses due to the ohmic losses, and losses due to the radiation from the sphere. And this is the negative part of the or imaginary part of the this radiation resistance over here. So the total impedance of the antenna system is RR plus RL plus J of XA. Again one thing, there is a electric charge, or we can say the steady current is do not radiate the electromagnetic signal. Like if we consider a DC that is flowing, a large amount of DC or any magnitude of DC is flowing into the simple straight wire, it cannot radiate even if you are providing maximum amount of power. But as we make like in the straight wire DC, there is no radiation. But if we curve this wire and flowing the same amount of DC, some of the radiation goes out from this wire. So this curved path actually change the speed of the electron that is flowing into the straight wire. This change in the speed or change in the acceleration of the electron or deacceleration of the electron make the radiation happen. So the radiation is happen only in the two main category. Either we curve the wire and make the DC as it is, or we can change this DC to AC and consider the flat wire. So AC is again varying with the time, and due to the variation in the velocity of the electron due to the transmission of AC signal, there is a radiation. The two method is either you can bend the wire or you can flow the AC current into the wire so that the total radiation can take place. So the radiation that is coming out from the antenna is generally distinguished between three category, that is isotropic radiator, omnidirectional radiator or directional antenna. So in case of isotropic radiator, we consider a very point source over here in the space, and this point source is radiated in all the direction by an equal amount of power. So this point source, which is ideal case, there is an antenna which is point source and it radiate into the atmosphere, and it make the radiation as a sphere in all the direction uniformly. While in case of omnidirectional antenna can radiate the same amount of power in one particular axis, like in the x-axis. It is not uniform in the z-axis, but it is uniform in the xy plane. So in the xy plane, if there is a antenna that is dipole antenna and it radiates, it form this donut type structure across the complete xy axis in the xy plane, but this radiation is not uniform in the z direction. If it is uniform in the z direction, it became isotropic antenna. So that is the difference between isotropic antenna and omnidirectional antenna. In isotropic antenna or isotropic radiation, the radiation makes a sphere, while in omnidirectional antenna, it makes a donut type structure in the radiating plane, that is xy plane, and there is no radiation in the perpendicular axis. And the third antenna is known as directional antenna, which have only radiation in one particular direction, like in the across the y-axis over here, and there is no radiation in the x-axis and z-axis. So if we have the antenna over here, like this is a horn antenna, and the radiation pattern is like this in a particular direction, and this is known as the directional antenna. Why a point source is behave as a isotropic antenna, and a dipole antenna, single small element, is behave as a omnidirectional antenna. Now this is again the equation, that is I of L is equal to Q of V, that is I is the time changing current, either the current is AC, L is the length of the wire, or we can say charge is equal to q and v is the time change of the velocity. The time change of the velocity happen if the charge is q is flowing, then we have to bend the wire. So either you flow the AC current or you make the bending of the wire so the velocity gets changed. We can basically radiate the electromagnetic signal into the space. Another thing is when the electromagnetic waves coming from the antenna, it makes like this type of structure, that is the wavefront is not completely flat, but it is spherical in shape. But when we cover the large distance up to the receiving antenna, this wavefront get bigger and bigger and get almost flat at the receiving end, and the receiving antenna having a very less dimension in compared to this wavefront, which is coming from 50s of kilometer. So that's why this wavefront, a small amount of power is received, which is proportional to the aperture of this antenna that is received. That's why we need a amplifier which is very much after the receiving antenna, and then the signal goes to the receiver. So wavefront is actually circle which became flat due to the large distance from the antenna. So these are the different transmitting zone of the antenna. This is field zone, and this is divided into three categories: near field or frictional zone, far field, and there is one more in the near field. There is again two things, that is radiative near field and reactive near field and radiative near field. This is known as the near field region or frictional region, this complete, and this outer region which is out from the R2, this is known as the far field region. So there is three type of zone of the radiation near to the antenna. Which is very near to the antenna is known as reactive zone. In this R1, the magnetic field as well as the electric field both are dominant, and this is due to this magnetic current. This radiation is very much non-uniform over here and almost of no use for the user. While in the near field radiative zone, it is represented by the formula R2 is equal to 2d square by lambda, where d square is nothing but the dimension of the antenna, this dimension of the antenna, d square by lambda, in which we can receive the radiation, but it is again not linear. It is some having the non-linear component. But after this R2, this is known as far field region or Fraunhofer region. In this region, there is a radiation which is very much uniform in all the direction from the antenna. So these three fields are represented by antenna field regions, and R1 is also calculated with the help of formula 0.62 under root of d cube by lambda. So these are the scenario that what is the wave looks like for non-radiative reactive region, in which the magnetic field dominate compared to the electric field, and the field structure looks like this. In the radiative field, there is large amount of radiation but less amount of radiative field, and in the far field only the radiative field or circular wavefront is present, as we can see over here. Now these are the different antenna parameters: radiation resistance, directivity, radiation resistance, efficiency, gain, bandwidth, reciprocity theorem, and many more. And we will discuss these 5 over here in this lecture, and these are in the next lecture. So the first one is the radiation pattern. Radiation pattern is the electric field pattern that is radiated by the particular antenna or by a particular design of the antenna, and it is represented in the theta, phi, and spherical coordinate system, r theta phi coordinate system, in which we can see this is x axis, this is y axis, and this is z axis, and this is angle theta is equal to 0, and this is angle phi is equal to 0, and phi is moving in the xy plane as this. Phi is equal to 0, 10, 20, 90, and in this way. So the total variation in the phi is equal to 360 degree, while total variation in the theta is equal to from positive z axis to negative z axis, that is 180 degree, and this is the r vector that is coming out from the origin towards the space, that is represented by p point over here. Okay, so the total radiation field, if the antenna is over here, the field is radiated in the positive z direction, and this is the main lobe of the radiation, and these are the different side lobes, and this is the back lobe of the radiation. As we want to transmit most of the power in the desired direction, but due to the imperfect matching due to with the space or defects in the antenna design, these side lobes can generate which radiate the power in the unwanted direction. So the best scenario for the antenna designer is to increase the main lobe radiation and decrease the side lobe level. We can only decrease the side lobe level, we cannot ideally remove that side lobe. If it is removed completely, then this is the scenario of ideal case. So this is the electric field vector. This is E theta vector in the direction of theta. This is E phi vector in the direction of phi, and this is ER vector, which is not represented here, which is coming out from the R direction. So these are the description as we already told over here. Now, if we cut this radiation 3D radiation pattern into 2D, the scenario is looks like this. This is 0 dB maximum distance, and this is minus 3 dB point. Minus 3 dB point is the point that is the power is going to be half from the center power. So if the power is power here is equal to 1 and 1 watt, and at this point the power became 1 by 2 watt. So we convert this 1 by 2 watt into the dB scale. So for the 1 it is 0 dB, and for 1 by 2 it is minus 3 dB down with compared to this 0 dB, or we can say for 0 dB it is minus 3 dB. Let's suppose if the power is 10 dB, then this point is 7 dB, up at the point 7 dB, 7 dB in this direction and 7 dB is in this direction. So when the power goes down by an amount of 3 dB, that angle over which this power goes down, this angle is known as the half power beam width of the antenna, and it is represented by HPBW, half power beam width. The second beam width is equal to first null beam width. In the first null beam width, where this is the main lobe and the first time the power get 0. This is the side lobe. Again we have the power, again we have the power in this direction, but in this direction there is no power. And this happens first time from theta is equal to 0 if we move in this direction. So first time when the theta, at a particular theta, this power became 0. So the gap between this point to this point in the opposite direction, this is known as first null, not full, this is first null beam width. First null beam width, and it is represented by FNBW, and these are the side lobes. And again the side lobe must not be greater than minus 20 dB marks. If it is greater than minus 20 dB mark, it behave like it is another main lobe. So always be careful while designing an antenna that the side lobe level radiated by the antenna must be below minus 20 dB mark. This is the radiation pattern again represented into the rectangular coordinate system. So this is the main lobe, and this is the half power beam width where power became half of the maximum value, like 40 degrees over here. And this is the first null beam width where the power goes 0 first time from the center of the main beam. This is first null beam width in the rectangular coordinate system. This is the side lobe level 1, which is at minus 9 dB. Side lobe level 2, this is at minus 13 dB, side lobe level 3, 4 and so on, and this is the back lobe. The power pattern and the field pattern is also represented in the same scenario, and it is related as power pattern is nothing but field pattern square. P and theta is equal to E and square theta over here. So this is the half power beam width, first null beam width for the same electric field pattern and the power pattern. Power pattern, the power became half. In the electric field, as this is the square, the electric field became 0.707 times. That is 1 upon under root 2 times of the maximum electric field available over here. So these are the beam width as we already explained. A normalized field pattern, if we divide the field pattern by its maximum value, the value became normalized. So, all it is always less than 1 because this is the maximum value. So, it is always less than 1 and this is a dimensionless quantity, normalized power, and it is represented by this. It is normalized electric field and this is for the normalized power, as we can see over here. This is a small example of half power beamwidth, how we can calculate the half power beamwidth for the given radiation pattern. This is the radiation pattern of cos square theta. So, if we put cos square theta is equal to 0.707, where the power became half or electric field became 0.707 times of the maximum value, we put this cos square theta is equal to 0.707 for the half power beamwidth and calculate the theta, and we get a theta is equal to 33 degree, which is half of this value. So, for the complete half power beamwidth, it is twice of theta, that is twice of theta, 66 degree. So, if you have the electric field pattern or the power pattern, we are able to calculate the half power beamwidth by putting that value to either 0.707 for the electric field pattern and for the power pattern 0.5. This is the beam representation in the 3D scenario. This is the theta variation, this is the phi variation, this is the theta variation, and this is the projection of this r over the phi direction. This is the variation d phi and this is r sin theta, and this point is became r sin theta into d phi variation, and this is r, constant r, and change in the theta from this point to this point d theta. So, this area is known as the beam area and it is represented by r square, that is r sin theta multiplied by r d theta, that is r square sin theta d phi, or we can represent it as r square d ohm, this value, this is d ohm. So, this dA, this small area in the 3D radiation pattern is represented by r into d ohm, where d ohm is the solid angle. Solid angle is nothing but it is the 2D representation of the 3D angle, and it is represented by either in steradian or in square degrees. So, the total area of the sphere is nothing but 2 pi r square integration from 0 to pi for the theta sin theta d phi, that is minus cos square theta, and if we put the value from 0 to pi, that is 4 pi r square. This is the beam area of the sphere, which is nothing but the volume of the which is nothing but the surface area of the sphere. So, if we calculate the steradian in square degree, we have to use this formula. 1 square radian or 1 steradian is nothing but 180 divided by pi whole square degree square, that is square degree. It is equal to 3282.8 square degrees. So, 4 steradian, that is total angle of the sphere, total solid angle of the square in square degree. This is 4 steradian is nothing but 41,253 square degrees. So, this 3D angle is known as the square angle, or it is represented in square degrees. This 3D angle, this 3D cut, this 3D section of the sphere is known as the square angle. The beam area is now calculated. Phi is varying from 0 to 2 pi. Theta is varying from 0 to 2 pi. If we have the power pattern, normalized power pattern, we can put over here, and this is the differential area sin theta d theta v phi, or we can say the beam area. So, if we represent this thing, this is nothing but the double integration over the complete sphere. So, double integration for phi variation and theta variation, this is equal to 4 pi normalized power into d3 phi. So, we can calculate in terms of half power beamwidth in the theta plane, half power beamwidth in the phi plane. In the phi plane, in the theta plane, if we multiply these two, this became a beam area. So, the total radiated power, we can calculate the total radiated power by the Poynting vector. Poynting vector is nothing but the electric field representation multiplied by the magnetic field representation. So, the total power is equal to this watt power into differential surface ds. So, the total power is equal to this. So the total power is represented by, in terms of electric field, is the real part of E cross H star. E is the electric field, H is the magnetic field का complex conjugate into ds times. Radiation intensity is nothing but the radiation density multiplied by r square, that is the distance from the transmitting antenna. Then the total power is equal to radiation intensity into sin theta d theta d phi. Then beam efficiency. So if we have the beam like this and we have the side lobes or side beam like this, so we have the beam area of the main beam and beam area of all the side beams is equal to the beam efficiency. So beam efficiency, main beam area over total beam area, all the side beam, and strip factor is the opposite of the beam efficiency, which is the side lobes beam area divided by total beam area, strip factor. So the directivity is represented by the maximum power in a particular direction over the average power. So like if we have the directional antenna and have the radiation pattern like this in particular direction, and the same amount of power P is radiated by a isotropic radiator P in all the direction. So the power is same. So direction, the radiation in a particular direction over the complete sphere is the ratio, and this ratio is represented by directivity P theta phi max upon P average value. So you can calculate with the help of solid angle as well. So these are the different representation of the directivity. For the half beam area or semicircle, we have the directivity of 4 pi divided by 2 pi, that is equal to 2. Gain of the antenna is represented as K times of directivity, where K is the loss factor. Directivity is the ideal value, gain is the practical value, and K is the loss factor. So if we decrease the loss from the directivity, we can find the gain of the antenna. This representation, this directivity is represented also in the square degree as this square degree divided by half power beamwidth in theta and phi planes. So this is nothing but 20 dBi for the 20 cross 20 dB half power beamwidth in theta and phi planes. So thank you. These are the different parameters of the antenna that we will discuss in over here. We have one more topic where we transmit the wave from transmitting antenna to the receiving antenna, and we deal with the power and drive the fringe transmission formula. Thank you for this lecture.